Hello everyone, let us discuss a very interesting question, and this question is asked in the TIFR Mathematics PhD Entrance Exam 2025. This question is from the real analysis part. In this question, what is given? Given fn is a sequence of functions whose domain and range are both real numbers, means sequences are real valued sequences, and this sequence satisfies these two conditions. First one is this one: integral from 0 to 1 fn x dx is equal to 0 for all n, and the derivative of fn dash is less than equal to x to the power minus half for all x belongs to the 0 open interval 1 close interval, and these functions are differentiable function. Okay, what is asking? This sequence of function is uniformly bounded or not, and this sequence of function has a convergent subsequence or not. These two things we have to verify. For that time being, believe me that these two things are true. Okay, means I will prove that these both statements 1 and statements 2 are true. But before going to prove the statement, first of all, you have to know some preliminary concepts. Okay, what is the meaning of uniformly bounded? Okay, means to solve this question, we are mainly apply a standard, very standard real analysis theorem. It is called the Argela-Ascoli theorem. Argela-Ascoli theorem. To understand the Argela-Ascoli theorem, you have to know about the meaning of uniformly bounded and equicontinuous. These two concepts are required. If you do not know, then pause this video and try to learn the concept, then come to this video. Okay, if you are well acquainted with the uniformly bounded thing and the equicontinuous thing, then stay with us. Okay, so if you do not know, let me give some brief idea about the uniformly bounded. What is the meaning of uniformly bounded? A sequence of function is uniformly bounded if fn x modulus, okay, is less than equal to, if there exists a m greater than 0 such that this is true for all the n and for the all the x belongs to 0 to 1. We have to verify in this question, we have to verify for 0 to 1, for all x belongs to 0 to 1, and for all n greater than equal to 1, this should be true. Then we called that sequence of function is uniformly bounded. Now I will move to the definition of equicontinuous. Equicontinuous is like one type of uniformly continuous. Means in the uniformly continuous, you know that fn x minus fn y mod for a given epsilon greater than 0, if we can find a delta such that fn x minus fn y mod less than epsilon for all x minus y mod less than delta. This is the definition of and the delta is independent of the point xy. Okay, means for a given epsilon greater than 0, if we can find a delta greater than 0 such that this will happen, we called that for a fixed n, then we called it a uniformly continuous function. But it is not the uniformly continuous function, it is the uniformly equicontinuous. Means there is some extra thing, that because here there is no one function. Uniformly continuous function concept is for the single function, but here the family fn is coming. So if this uniformly concept is true for every n, means this epsilon is and delta are both means if this delta is also independent of n, then we can say that this family is equicontinuous. Are you getting my point? Means I am saying that uniformly continuous function concept is for a one function, but if this delta is true for all the function n, when n varies from 1 to infinity, if this is true, then we called that family is equicontinuous. So it is the generalization of the uniformly continuous function, therefore it is called the uniformly equicontinuous. Okay, I hope that you all get it. So if you do not know, then read this definition 1. This is for the uniformly bounded sequence and this is for the uniformly equicontinuous sequence. And the Arzelà-Scully theorem says what? If a family of sequence of continuous functions, it requires continuous function, but in our question these functions are differentiable, so these are also continuous. There is no problem. If there is a sequence of continuous function and that sequence is uniformly bounded and equicontinuous, then Arzelà-Scully theorem states what? Arzelà-Scully theorem says that it has a convergent subsequence, uniformly convergent subsequence. Okay, then this statement 2 will also be true if we can show that it is uniformly bounded and equicontinuous. Okay, let us proceed to prove the uniformly bounded and uniform equicontinuity. Okay, first I will prove the uniformly equicontinuity. First I will show that this sequence fn, this family fn, n greater than equal to 1 is equicontinuous. Okay, let us proceed to prove. But equicontinuous on which domain? It is not asking for the for whole R. In the question it is asking only the 0 1. So in our discussion every point xy we will consider they all lie in the closed interval 0 to 1, because our question is on the 0 to 1 closed interval. So we are taking x and y on the 0 1 closed interval so that y is less than equal to x, because x and y are two numbers, either y will be less than equal to x or x will be less than equal to y. So we are without loss of generality we are taking y is less than equal to x. Okay, then we will find this modulus. To show the equicontinuity we show that this this quantity is less than epsilon. We will take later, but we will start from this thing because we are going to prove the equicontinuity property. Okay, so this thing can be rewritten in this way, because when the derivative and integration cancel out, it gives fn x minus f of y, fn y. Okay, so then we in the next step we will take the modulus inside, so there is less than equal to is sign is coming. Okay, and we know that fn dash z modulus is less than equal to z to the power minus half. It comes from our question here. This is given from equation 1. By using equation 1 we can estimate this fn z dash by z to the power minus half. Then after integration it gives this one. Okay, this is equal to 2 into x to the power half and y to the power half, and here our x is greater than equal to y. Then we will apply a simple real analysis inequality. It says that if 0 is less than equal to n and less than equal to b and alpha will lie in 0 to 1, then this inequality is true. Here our alpha is equal to half. Okay, this inequality can be proved by using the mean value theorem. You can simply prove it. It is your homework. You have to prove this. Okay, for the time being believe me that this is true. Okay, therefore this quantity can be estimated by using this inequality. So we reach to this step. Okay, and since our x is greater than equal to y, so there is no harm to put its also modulus sign. Okay, so we prove this thing. So we establish this step for x greater than equal to y. Similarly, if one will take the x less than equal to y and proceed the similar steps, we can prove this estimate. Okay, and this estimate implies that our sequence is uniformly equicontinuous. How? Suppose we are taking any epsilon greater than 0, then we can find delta, because we can take this less than epsilon, then we can find delta x minus y mod less than equal to epsilon by 2 square root comes out right hand side, it will give square. If we take this delta, and this delta is independent of x, y and n, so we are getting for every epsilon we are getting a delta is equal to this one, epsilon by 2 whole square, and this delta is independent of n. It works for the every function. Therefore our family is equicontinuous. Okay, so it implies our family is equicontinuous. So we proved that our family is equicontinuous. So our next task is to prove that it is uniformly bounded. Okay, So but our discussion is on this 0 1 close interval. So we are taking x belongs to 0 1 close interval, then we are adding and subtracting fn 0. Okay, then we will apply the triangle inequality, then we will reach to this step. Now we will estimate this term and this term separately. Okay, first we will taking this term, this one. Okay, so from the step 2, from the equicontinuous step 2, this is the reason why I prove first equicontinuity. I did not proceed to prove the uniformly boundedness first, because after proving the uniform equicontinuity, then I can use this step 2 to prove the uniformly bounded. Therefore I proved uniform equicontinuity first, now I am proving the uniformly bounded. Means this quantity is less than equal to this, and this is coming from the step 2. Okay, because step 2, and for x equal to x and y equal to 0, if we put y equal to 0 in this step you will reach to this step. Okay, then this is nothing equal to this one, and since our x lie between 0 to 1 compact interval and its highest value is 1, then it can be denominated by 2 times 2. Okay, therefore we estimate this term. Now we will proceed to estimate fn0 modulus. Okay, this also comes from this step. Okay, if you open this step, then it will give this one, because this modulus is less than equal to 2. So this quantity fnx minus fn0 lies between -1 to -2 to +2. Okay, then add minus fnx on all the terms, then we will reach to this step. Okay, then multiply the minus sign in this inequality, then it turns out to be this one. Okay, then after that take the integration from 0 to 1 on each term. Okay, because integration satisfies the inequality concept. Means if f is less than equal to g, then integration of e is less than equal to integration of g. So there is no harm to take the integration on all these terms. Okay, but here and integration is from 0 to 1, and here -2 is a constant, and integration from 0 to 1 will give 1, so it is -2 only, and similarly it is +2. Okay, but we know that the in the given question, means in the equation 1, here it is in the given question, it is given that integration of fnx from 0 to 1 is equal to 0. So we will put here, so this quantity will vanish to 0, and this quantity will also vanish to 0. So it gives this one. It implies what? Modulus of fn0 is bounded by 2. Okay, so we will finally estimate also the second term, means put it in equation 5. Therefore using 5 and 4 in the equation 3, we will get fnx modulus is bounded by 2 plus 2, which is equal to 4. So and since our x is arbitrary point in the interval 0 to 1 closed interval, and for it is true for all n greater than equal to 1, therefore this sequence of family is uniformly bounded on the closed interval 0 to 1. Means we proved that our sequence of family is uniformly bounded, and it is also uniformly equicontinuous. So by the Arzelà-Ascoli theorem, this statement, theorem 1, it says that it has a uniformly convergent subsequence. Therefore this statement 2 is true. Which one? Therefore this statement 2 is true, and we have already proved that our sequence is also uniformly bounded. This statement is also true. Okay, so option A is saying it 1 and 2 both are true. This implies it is true. It is saying 2 is false, both 1 and 2 false, it is false. It is saying that 2 is false, it is false, and it is saying 1 is false, 2 is true, it is also false. I hope that you all understood it very well. Thank you all.